Here is powdered tungsten ore being screened so that undesirable particles will not be present in the finished filament wire. The filament, you know, is the wire that glows and gives us light. The attendant is weighing a pound of the grayish-black tungsten powder, which he pours into a steel mold. This mold is then placed under a tremendous hydraulic machine and subjected to a pressure of 15 tons per square inch. When the end pins are taken out and the lid removed, you have a bar of very brittle tungsten 2 feet long and 3/8 of an inch square. To eliminate the fragility of the tungsten bar, it is now annealed in this electric treating bottle. Before it comes out, it receives treatment at better than 3,000 degrees centigrade. After the bar has cooled sufficiently, it is removed from the furnace and is ready for swaging. This bar will soon be stretched into a piece of wire many miles in length, or enough to make over 35,000 60-watt lamp filaments. Under intense heat, the bar becomes pliable, and while in this state is forced into a series of reducing dies. Again and again it is forced in, each time through a die smaller in size than the preceding one. Thinner and thinner and longer, it has given up its shape as a bar and has become a rod 25 feet long as it forces its way into this fire chamber. What an inferno! The wire is finally reduced to a size where it may be wound on spools like thread. In this room it is drawn to sizes needed for lamp assembly. Different sized lamps, you know, take different sized wire. Here is the last machine on one of the rows. It is drawing wire that is finer by far than a human hair. No matter how good your eyesight, you can't see the wire. Let our pointer show you, and then take our word that the wire is there. The drawn tungsten wire does not escape the most rigid and minute examination. These 3 inspectors are checking wire diameter, and odd as it may seem, they are telling wire by weight. This girl is measuring a length of the finished filament wire. This done, she cuts and twists it in such a fashion that it will hang in the torsion balance apparatus. This balance is so sensitive that it can read the weight of a pencil mark. By knowing the length and weight of a given piece of wire, the inspector can tell if it is labeled properly for the lamp in which it will be used. Wire diameter must be constant throughout. This instrument, called an optometer, reads wire roundness to the thousandth of an inch. These are the machines on which the filament is coiled, the wire being wound around another wire called mandrel, which is later dissolved. As the mandrel wire moves toward the right, the filament wire winds around it like thread around your finger. Just imagine getting 1,000 turns of thread around 1 inch of your finger. That's what this machine does while it travels 11,000 turns every minute. The only thing asked of this peppy little machine is that it cuts the coil filaments to just the right length. Snip, 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 snip. No wire must be more than a fraction of 1% over or under its specified length, or it will be rejected. At this point, we must get rid of the core or mandrel wire around which the filament is coiled. To do this, the filaments are placed in a large tungsten coil. The coil is placed in a series of acid solutions. which eat out the mandrel but leave the coils unscathed. After the bath, they must be dried, of course. Sintering also removes any remaining impurities. Filament length inspection is very, very severe. A minute deviation, either too long or too short, and the wire is cast aside. Filaments are checked not only for length, but for defects in coil construction. This device is called a balloptica. By means of a series of enlarging lenses, the filaments are magnified many times on a ground glass screen. Any little blemish is quickly detected by this trained lady detective, and out goes the culprit. There is still another type of wire used in electric incandescent lamps, called leading-in wire. There are two of them in every lamp. They are the wires to which the filament is attached and which carry the current to it from the base. Copper and nickel are generally employed, and where the lead wire goes through the glass seal, a special wire having the same expansion characteristics as the glass must be used. Otherwise, the seal would break or leak as the wire heated up. This special part is called the weld, and the wire from which it is made is known as dumet, or two metals. The rod is brazed in this furnace. Here is a rod of dumet, made from copper and nickel steel. It is being swaged preparatory to the first drawing. Then drawing starts. Unlike the drawing of tungsten wire, which is done under intense heat, dumet is drawn cold. Just watch the rod lengthen as it is pulled through successively smaller dies, 7 of them in all. Smaller and smaller becomes the wire diameter. Now it has become so long that it must be coiled on huge spools. A short time ago, this was only a small, useless-looking metal rod. The wire is being drawn constantly finer as it is pulled through this soapy bath. But the dumet wire is still not fine enough, and so it travels on its way through another cold bath and a series of diamond dies. It is about finished now, when it will be wound on spools ready for delivery to the department which makes the leading-in wires. When the wire is to size, it is passed through a borax solution to prevent the wire from oxidizing and to keep it ducted. Looking for defects. A black mark on the wire is a black mark against it. On this floor, the leading-in wires are made. The lead wires, you will recall, convey the current to the filament. They are generally made of a piece of copper and a piece of nickel with a short section of dumet wire in the center. One of these welding machines has more than 2,500 parts, and when you see it in action, you have a much better idea of perpetual motion. This will give you a closer view of this lightning-like mechanism. Nickel wire on spools is fed into the machine from the left, and copper wire on spools from the right. You can see plainly there the action of the wire on the right as it rushes in to be welded to the other materials. The dumet is fed in from above, and every time the rocker arm swings down into position, a percussion weld is made, dumet to nickel and dumet to copper. As we slow the machine down, you can see the flash as the weld is consummated. You are observing one of the most intricate of operations in the manufacture of lamps. This machine makes as many as 100,000 lead wires a day, every one of which is rigidly inspected before it goes to the lamp factories. Trained eyes count as they inspect. Lead wires are so important to a lamp that only perfect ones can be used. Here is a number of the finished lead wires consisting of copper, nickel, and dumac. And here is just one of them. My pencil is pointing to the all-important weld. Even low wattage lamps are now filled with an inert gas so that they will burn brighter and more efficiently. Argon, which constitutes less than 1% of the Earth's atmosphere, is the kind used. The argon contained in these tanks is practically 100% pure and is introduced just before the lamp is sealed off. Here is a modern miracle, a machine which makes the very heart of the lamp. It is many times more complicated than your watch, but just as accurate. Here is a bin containing flanges which are fed into the machine automatically, one at a time. If they start to fight for first chance, this persistent little duster separates them. 2 lead wires are placed into position inside the flange tubing as the machine goes merrily on its way around the circuit. This bin contains another piece of glass known as stem or exhaust tubing, and this part too is automatically fed into the machine. Heat is applied to the flange as the machine rotates, each fire making the straight end of the flange softer and softer and softer. Then a seal forms which fuses the straight end of the flange and the center of the exhaust tubing around that part of the lead wire which we show you as the well. The single unit is now known as the stem. The reason you no longer have sharp tips on the lamps you use is because the air is now exhausted from the bottom of the bulb. To do this, a hole is blown just below the seal. Puff, puff, and it's a simple operation, isn't it? Here the so-called buttons and supporting hooks are applied. You can see these two things happening simultaneously. At the end of the stem tubing, a small flat button is made, and at the very same instant, 3 short supporting hooks for the filament are embedded in the softened glass. To ensure a better clamp for the filament, the ends of the lead wires are flattened. Then a hook is made in each flattened part. Within this hook, the filament will finally but firmly be clamped. This girl is placing the coiled filaments in position so that one by one they will be fed in place for mounting on the lead wires and supporting hooks. This bracket arm drops the filament into place. The support wires curl up around the filament, which is then clamped to the lead wire. If the first clamp wasn't perfect, this one makes it so. Around the conveyor and off of it they come, 1,300 an hour. Mounts, 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 and more mounts. The heart of every Mazda lamp is this rugged frame of glass and wire. And every one a perfect mount, one so perfect that only machinery can build it. Machinery that ingenious General Electric engineers are constantly making better. Getter is a liquid substance which is applied to the filaments of all gas-filled lamps. This chemical facilitates proper exhaust by burning up all loose air particles in the bulb, and a lamp that is entirely free of air will not blacken readily in use. These filaments have now been gettered. With a finished mount and a bulb, we are now ready to complete the lamp. There are two tiers on this machine. The operator places a mount into a chuck and a bulb onto the revolving wheel at the right, and then they start on their way. Before the bulb drops over the mount, the GE monogram, GE in a circle, is stamped on the end of it. Then the bulb drops down to the lower tier and over one of the mounts. And the GE monogram is burned in because we are very proud of it. When the glass is heated and softened to just the right degree, this clamp comes around and forms a perfect shoulder on which the base may be fitted properly. Heat and gravity cause the superfluous glass beneath the shoulder to break loose and drop from the lamp. The lamp is now ready to be placed in the lower tier for exhaustion. As the lamp travels around on this machine, it gets a succession of evacuations and nitrogen gas flushes. The operation is similar to the washing of clothes in a laundry machine. It is not until the last stage that the lamp is filled with argon gas. Only the base is lacking for the finished job. Lamp bases are not ready for use until a special basing cement is applied around the inside. The cement enables the base to fit fast to the glass and metal and so prevents looseness. When this smiling lassie gets the trays filled, they will go to the basing machine, which you see right here. Notice that two ends of the lead wire still project from the neck of the lamp. This operation straightens them. The leading in wires must be cut to just the proper length. Now one wire is soldered to the shell of the base and the other to the brass eyelet in the center, which is insulated from the shell. Before the lamps come off the machine, they get a voltage inspection, being tested over normal voltage so that any defect will cause immediate burnout. As the lamp flashes, the getter also becomes active. After the lamps are packed, there are still other checks on quality. These tests are made by the Electrical Testing Laboratory of New York City on 5% of all lamps. Here is some of the inspection tables where these lamps are judged for 150 possible defects, including loose and crooked bases, loose filament wire, overall length, life, and filament strength. This device, for example, tells quickly whether the base connection with the bulb is rigid and strong. A 60-watt lamp must not be more than 4 millimeters over or under its designed length. This eccentricity test tells whether the bulb is properly centered with the base. If it fluctuates more than 5 degrees while rotating, the lamp is rejected and the entire case of lamps laid aside for complete inspection. Let's go into the laboratory, which is dedicated to the task of making Mazda lamps constantly better. Dozens of laboratories like this are solving tantalizing problems. From this one possibly may come better finishes for the inside frosted and colored lamps. This experimental laboratory, the first and largest of its kind in the world, takes all the guesswork out of factory production. All new types of lamps and all new lamp-making machinery get the acid test here under actual manufacturing conditions before being released to our factories. This is just one of the many precautions taken to assure the consumer of getting lamps that are worthy to bear the mark Mazda and the famous GE monogram. Burned to death. Every day lamps come here from our factories and are placed in these racks to burn, burn, burn. Long, bright light is a requisite of Mazda service. This is a spherical photometer. What a contrast to Edison's Bunsen photometer. The inspector places a lamp in the center of this large, tightly sealed sphere. Then, with the aid of the photoelectric tube and voltage balances, she is enabled to read the recording instruments in a jiffy. They tell whether the lamp will burn at its rated voltage, amperage, and wattage. This is important to you because lighting costs are dependent upon these three factors. A Ferris wheel. But if you ride in this one, you'll get bounced around a bit. This is a gravity impact tester, and its purpose is to test the strength of the filaments so that ways may be devised for improving them. 80 hard bumps and still able to light. This is the test, and few fail. Lamps of today are more than 10 times as efficient as those of 1879. But scientists and engineers press on, ever seeking ways and means to make the lamps of tomorrow better in quality and more economical in use than even the Mazda lamps that light the world today.